In this video, we're going to see how a measurement that looks like an entangled measurement because it's performing projections in the Bell basis can in fact be implemented by Alice and Bob using only local measurements and classical communication. So let's recall the setup. Our goal was for Alice and Bob to implement the projection pi, which is the projection on the EPR pair, phi plus, where phi plus is equal to 1 by root 2, 0, 0 plus 1 by root 2, 1, 1. So that's our goal. And we said, look, if you want to do this, you can decompose it into two different projections. There was projection A, which we can call pi A, and that would be the projection on phi plus phi A, where the state phi A is 1 by root 2, 0, 1 plus 1 by root 2, 1, 0, and the projection pi B, which projects on phi plus and phi B, where phi B is the state 1 by root 2, 0, 0 minus 1 by root 2, 1, 1. And I claim that each of these two tests was equivalent to measuring for test A in the computational basis and checking agreement of outcomes, and for test B in the Hadamard basis and checking agreement of outcomes. Let's see why. Let's do it for test B. So you know that the Hadamard basis, the two basis states, plus and minus, they're eigenstates of the X operator, the Pauli X, which is this operator here, plus with a plus 1 eigenvalue, minus with a minus 1 eigenvalue. So what the test that corresponds to measuring in the Hadamard basis and checking agreement of outcomes is doing is that it's doing the following. It's testing that the state psi that Alice and Bob are sharing, so verifying that when you make the measurement in Hadamard basis, you get the same outcomes. This is equivalent to checking that the state that you're sharing is an eigenstate with eigenvalue 1 of the corresponding tensor product of Pauli operators. Now, what are the eigenstates of eigenvalue 1 of xa tensor xb? Well, you either take an eigenstate of xa with eigenvalue 1 and an eigenstate of xb with eigenvalue 1, or two eigenstates with eigenvalue minus 1. So the eigenstates that you have are either tensor plus or minus tensor minus. And so this is what this test is implementing. It's implementing the projection on the span of the plus tensor plus and the minus tensor minus states. So this is not what I claimed. I claimed that it was implementing the projector on the span of phi plus and phi A. But these are equivalent, because if I take the sum of plus minus minus, and I normalize by 1 by root 2, what do I get? Exactly phi plus. And if I take their difference now, 1 by root 2 plus minus minus minus, what do I get? Well, you can check, and the state that you get is exactly the state phi A. So the span of plus and the span of minus minus is the same as the span of phi plus and the span of phi plus and phi A. And so this is what, when Alice and Bob are checking that when they measure in the Hadamard basis, they get the same outcome, they're in fact doing something which is equivalent to implementing the projection on the span of phi plus and phi A. And similarly, you can check that when they're making the checks in the computational basis, then this is equivalent to performing the projector on the span of phi plus and phi B. So that jointly, these two tests are equivalent to performing a rank 1 projection on phi plus, to checking that the state between Alice and Bob is entangled. So of course this is just a different way of thinking about the protocol, and in fact we're going to prove security using slightly different arguments. But it gives you a good intuition as to why these tests are important. Why do they enable security? Because they are checking that Alice and Bob are maximally entangled. And if Alice and Bob are maximally entangled, then by monogamy it means that their information cannot be shared with any eavesdropper Eve. So that's the basis for security.